Thank you all for joining us today. It's a beautiful day outside in Seattle, so thank you for being inside here. We are graced with Lauren Conger's presence today. She is a PhD student coming from Caltech and has been visiting for a couple of days. And today she'll be talking to us about some recent work at the intersection of game theory, optimization, and controls. So go ahead and let you take it away.
Thanks, Nick. Thank you for the opportunity to have me give a talk and for hosting me. It's been a really nice visit. So today I will be talking about multi-species Wasserstein-2 gradient flows. And this work is, oh no, clicker. Okay. This work is kind of a summary of 4 different papers, most of which has been done with these 4 wonderful collaborators. So Franca and Eric are 2 of my advisors at Caltech. Franca's expertise is in PDE regularity theory, among many other things. Eric's is in game theory and learning. And then Lily Ratliff here at University of Washington has contributed from the game theory side. And Ricardo Baptista from Caltech worked on some of the optimal transport applications that we've been looking at. And just to point out, the monotone flows paper is very new, so you guys are among the first to hear the hot off the press news, so I'm very excited. Okay, so one question that we're interested in is how do we model people behaving strategically? So we look at this data set from Columbia, and people submit their census data. So we have a worker come to someone's house and collect things like how many TVs do you have in your room? How many rooms does your house have? How many people live here? And all of this data is combined into a poverty index score. And if you're below this red threshold, you qualify for certain government aid programs. And you can see that for 3 years, the distribution is somewhat Gaussian, maybe not exactly Gaussian, but looks pretty standard. And then in 1997, the government releases the information of what the threshold is and how the poverty index scores are being computed. Okay, so what happens in 1998 is that we see a strategic behavior distribution shift where a number of folks who are close to this threshold manage to manipulate their data to be under the poverty index score. And actually this paper from which we took the data explains that local officials misrepresented what the minimum wage was in many different areas in order for this to occur. And we see over time even more strategic behavior, and eventually a large fraction of the population is below this threshold. And we want to be able to model this as a distribution. And so we ask, okay, is this something we can model as a gradient flow? And there are lots of tools for this. However, one issue is that we have multiple species. So here, the government has the ability to change their threshold so they can behave strategically, as does the population of agents. And so a lot of our existing theory is for a single species, and we want to look at what happens if you have multiple strategic entities. Another application that we are looking at is optimal transport. So I have 2 measures, mu and nu, and so these color plots are their densities. And I would like to ask, okay, how do I optimally transport mass according to whatever cost function from one measure to another? And the way that we approach this is by solving a min-max problem. So instead of constraining the marginals to be exactly equal to mu and nu, we can have kind of a soft constraint here where there's a penalty for a marginal not matching mu, and a penalty for the other marginal not matching nu. And then we take a maximum over this lambda. And you can show that the equilibrium of this min-max problem is exactly the optimal transport problem. And so how do we solve this? We can use a gradient flow. So to solve this min-max problem, we take a step in the maximizing direction for lambda and a step in the minimizing direction for gamma. And here this is the gradient with respect to the Wasserstein-2 metric. So you can see this as the direction of steepest descent with respect to this particular metric. And I will kind of explain more about this in a bit. Again, we have another issue of multiple species. We have a gradient flow and we have multiple entities that are evolving. And so our current theory doesn't fit and enable us to analyze this yet. Okay, and a third reason why we care about multi-species gradient flows is banking and loans. So it's commonly known that fraudulent account requests are made frequently by bots or other entities, but most people are submitting, valid new account requests. This could also be for loans. So you submit your data for a loan, and the bank tells you yes or no. But you could also have multiple banks. So you could try, well, this bank one didn't give me a loan. I'm going to try bank two. And so you can model the applicants as distributions over their features. So what is your income? What is your age? How similar is your email account to your name? These are all data that go into a classifier algorithm that says whether or not you get approved for a new account or for a new loan. But it's also known that people manipulate these things over time. And I've even had a faculty member come up to me and tell me how he manipulated his data to apply for a loan after it was denied the first time. So many people are known to do this. And so we're going to look at a setting where we have two populations. So you can think of this as, income and this as your age, for example, or maybe more fittingly, number of months at your current residence, and two different bank classifiers. So this classifier X1 is saying everyone on this side should be approved, and this one is saying everyone on this side should be approved. So they're basically saying very opposite things from each other. And the orange is our valid population, and the blue is fraudulent. And so what this is telling us is that the second bank has a much better classifier because they're actually approving the people who should be approved. But this bank is doing exactly what it should not be doing. And if we allow them to evolve over time in a way that is consistent with their incentives. So for example, this blue population is incentivized to be on this side of the X1 classifier because then they can get approved from a bank, even though they shouldn't be, but that's their incentive. And so over time, we see this system evolving as both the classifiers are learning, but also the densities are evolving according to ways that benefit them to be approved. And again, we might want to ask, okay, under what conditions is the system stable? Will we converge to something? How much worse does bank one do than bank two? Or even how many fraudulent accounts are opened over time? And again, this is a setting where we have a multi-species PDE. And so we really need to build some analysis tools that allow us to answer these types of questions. Okay, so our objective is to characterize long-term behavior for multi-species PDEs that have the specific gradient flow form. The issue in general is that each species is being driven by a different energy. So this system is not a joint gradient flow. So we can't apply classical gradient flow results. And so the way that we address this is we take some ideas from game theory and optimization, which has a lot of literature in finite dimensions, and extend monotonicity, which is kind of a notion of convexity or dissipativity, to now a set of operators in this metric space. And so the key question that I will discuss today is, okay, can we develop monotonicity for gradient flows? And so I'll talk about three main contributions. One is just what is monotonicity for gradient flows? This is not clear because historically all of this has been defined on Hilbert spaces where you have an inner product and a norm. And for measures, you have neither. So the definition itself is a new contribution. I will then explain what results you can show based on this new definition, and then kind of show what insights you could get on those applications that I started with. Okay, so first I will define monotonicity, and then I want to kind of explain what related work we're building upon and kind of how this contributes both to the PDE analysis literature and also the game theory literature. I will give our long-time behavior results, which was the goal of why we define monotonicity, and then show some insights that we have in some of these applications. Okay, so first, monotonicity. So I want you to think of monotonicity in one of two ways. One way you can think about it is a condition for existence of a Nash equilibrium. So a Nash equilibrium is saying, is some rho star such that if I fix all of the other species, so you take the first player, if this is a game, you fix all the other species and you optimize over your own species, you get the Nash back. But then if you plug this value into the other players and they optimize over their own species, you still get the Nash back. So this is one way of viewing monotonicity. It's a sufficient condition where you know that such a solution exists. Or if you want to think about it more from a dynamical perspective, you can think of it as what does convexity look like in a multi-energy setting? So in this setting, each species 1 has some energy F1, species N has some energy Fn, and they are different from each other. And so we know what it means for F1 to be convex in row 1, but what does it mean for the entire system to be convex in row, in the vector of all of the rows? So you can think of monotonicity as kind of this generalization of displacement convexity for a multi-energy system. And so what this gives you really is contraction in some joint metric. But again, energies don't necessarily decay anymore because you have multiple energies and you can no longer say, you're not just solving for a single minimizer. Good. So to start with this definition, I want to give some intuition from finite dimensions. So we will look at a system with n species, and each player is a vector in Rd, or R sub di, and we're evolving our vector according to this velocity field. And we say that the velocity fields as a set are monotone if this inner product condition is satisfied. So if U was a single species, this actually looks very similar to what a convexity condition would look like. But now we have kind of a multi-species setting where we take all of the U's and we stack them up and then check if the inner product satisfies this criteria. Okay, so one of the nice features is that this condition allows us to show convergence of these two Lyapunov functions. And what we do in our work is extend these Lyapunov functions to the measure setting. And so I'm going to explain kind of how you show convergence for these two, and then show the analogous results for infinite dimensions. Okay, so how do you show convergence for this function? Well, let's take a time derivative of v, and we will end up with derivative of this product, and you have the derivative here, and then the other guy from the 2 norm, and we can plug in the definition of x dot here, and then we can apply our monotonicity inequality to then get contraction. So we have the velocity is bounded by the minus of the Lyapunov function. And then we can show something similar for v2, where we take a derivative, and then you can plug in the fact that this guy is 0, and monotonicity condition, get contraction. If you don't follow these steps, that's totally fine, but the main idea to take away is that monotonicity is a condition under which these two guys converge. And in finite dimensions, this is enough to say, okay, we have existence of a steady state or we have convergence to it. But in infinite dimensions, the notion of convergence or the notion of contraction depends a lot on what this value v actually is. Okay. So I'll give some infinite dimension examples. So these are the dynamics we'll be considering. So before we had some x dot being driven by some velocity field. Now we have some measure, rho I, which is a probability measure on RDI. And instead of x being evolved by a velocity field, we have now this velocity field driving the measure according to this function. So you can kind of think of this equation as analogous to this finite dimensional flow. And okay, what's an example? So if I wanted to do gradient descent on V, everybody's favorite algorithm, you take a gradient and then you set the derivative equal to minus gradient and you flow down. The equivalent for measures is you plug in the same gradient of that same velocity field here, and you have a divergence. So what does this look like? If I have some potential function, let's say this is my V, we expect the mass now to basically flow into the minimizers of this V. So the equivalent of gradient descent for measures now is that the mass is flowing into these minima. And then if I have maybe a log loss, which some of you might find very useful for your machine learning applications, you will see the mass kind of flowing into the minimizer, into the minimizer of this, which is basically just going off to minus infinity. So you see the mass starting to flow off. Another example you can look at, this is not directly equivalent, but you can kind of think of it as analogous, where this type of flow term is equivalent to driving your point to some reference x tilde. So this equation here drives x to x tilde in the same way that this flow drives rho to rho tilde. So if I set rho to be the initial condition, well, it's already at the reference measure, so it doesn't need to move, and it's just fixed. But if I pick a measure that is different than the initial condition, so here I have some Gaussian, and I want to, as a reference measure, move the Gaussian over and spread it out a little bit. Then I set this as my reference measure, and then the flow kind of does gradient descent, but in the measure sense, to flow our measure to its target distribution. Okay, so these are single species setting, but now I want to show a multi-species setting. Okay, so brace yourself for the what I've heard the Spanish call a chorizo equation. So you can maybe ignore this for now, but let's look at our dynamics. So we'll be doing a gradient descent on f, but f depends now on two measures, row 1 and row 2. And our other measure, row 2, will be doing gradient ascent. It's not, doesn't have a minus sign, it's going up on f on the same energy. And what we see is this kind of cycling, chasing behavior. And what I want to point out are a couple things. This kind of looks like a box because we have a quartic potential. So it's kind of like filling a quartic basin. This term acts like diffusion, so it kind of spreads the mass out, and it's the reason why our mass, which started kind of as a Gaussian, is getting wider and wider. And then this term is a coupling term, which means that one species is kind of chasing the other while the other one is kind of evading. And so this is why you see this cycling behavior in the measures where one is kind of running away from the other while being chased. So this is the type of PDE that we'll be studying and looking at and proving things about. Any questions? Okay. Okay, so this is our first contribution, which is the definition of what monotonicity is for infinite dimensions. So just as a reminder, this is what our finite dimensional dynamics look like in our inspiration. And this is what our gradient flow, or this is not necessarily gradient flow because there's no gradient, but okay, this is what our flow is. And we say that a set of velocity fields is lambda monotone if it satisfies this inequality where gamma is an optimal transport plan between two reference measures for any two reference measures in a particular set. I'm being a little sloppy with notation, so if anyone has any questions, feel free to ask, but I do not want to overload with definitions. And you can kind of compare this to our finite dimensional monotonicity, and you see that we have a very similar inequality on the inside of these integrals, but now we are integrating against this transport plan, which maps, there's a plan between this measure and this set of measures. Okay, so this is our definition of monotonicity. And for some of our analysis, we will look at the analogous Lyapunov functions. So here we looked at the norm of the velocity fields. Now we will look at the L2 norm of the velocity fields, but weighted by the measure. And then instead of looking at the convergence of x to some fixed point, we will now look at the convergence of rho to some steady state in this W2 metric. Any questions? Yes.
The goals of x of y supposed to be the lowest in that equation? With x minus y and then x minus y?
No, because here this divergence, if you plug things in, kind of acts like a minus sign when you do integration by parts. So that's why the sign here is flipped relative to this guy. Yeah. That's a good question, and that is something I had to check myself. Yeah. Yeah. Okay. So just to put some of this work in context, I will talk about what's already been done and kind of where our work fits into both game theory and PDE analysis. So, okay, in game theory literature, there has been a number of recent results, but also importantly, this very old, very relative, depending on, I guess, what field you're in, result about diagonally strict concave games. So this was the first notion of monotonicity, and this was done for Euclidean settings. But recently, monotonicity was kind of explored or utilized either for showing contraction of dynamical systems or for learning Nash equilibria in more of a computer science setting. And all of these were done in Hilbert spaces or something more specific. And so our work, because we're not in a Hilbert space, is at least as far as we know, the first work that is done in a metric space. And now that we've done it in the metric space, we're looking at, what does this look like in just general metric spaces? And then there's also been a lot of work on zero-sum games. And a lot of it has kind of been in the CS applied math area where people are looking at algorithms for solving min-max problems over measures. And in particular, this 2024 Colt paper asked an open question, which is, does this min-max problem converge? So if you have some functional f that depends on two measures, one player is maximizing, one player is minimizing, under what conditions do you converge to a steady state? And we answered this question in an earlier paper where we studied specifically a zero-sum setting and gave conditions under which this converges. And then you can later show that this is actually a special case of monotonicity. Zero-sum that have the right convexity concavity properties is a special case of monotone settings. In the PDE analysis side of things, there are lots of PDEs of this form, which I know a number of people in the audience have seen. And a lot of the related literature on this is on existence and characterization of solutions. So how regular is it is one of the main questions. I mean, there are some results here for what the long-term behavior does. It's usually on more specific choices of these interaction kernels. And so we kind of ask a more general question that maybe has more restrictions, but is more general. So this is a special case of what we're looking at, as long as you have enough regularity. And then some very recent works on like vector valued optimal transport or vector valued dissipation have come out. And so especially these Cavagnari, Savare, and Sodini papers, we use some of their results in improving our settings. Okay, so I will talk a little bit about the long-time behavior results. These are our dynamics, just as a reminder. We do require that the velocity field is in L2, and if anyone is curious as to kind of more specifics about our assumptions, please ask me. I kind of did not write that out in all their glory because they're a little bit much. So recall this finite dimensional inspiration. So we kind of can identify our W2 distance between some steady state and some measure as kind of analogous to saying, okay, well, how far is my current state away from some steady state? Okay, so we suppose that V is lambda monotone in some set. So this means that the monotonicity condition holds for all measures in some geodesically convex set A. We can show that there exists a unique steady state, and that if that set is compact, then the steady state is in the set. And so the way that you show this is you take two initial conditions and you show that they always contract to some steady state, and then this gives you an existence proof. And if we have the right behavior for rho infinity, that is, if you can show that it's in the same set, it doesn't leave the set, then you can show contraction of the W2 distance, the Wasserstein squared distance between rho and rho infinity. And a comment on this, this has to do with compactness, as I showed here, but even if you don't have compactness, we have some examples in our paper where A is maybe not compact, but you can show using Euler-Lagrange conditions or other conditions that the steady state is in fact in the right set. So this is not too much of a restriction. Okay. Any questions?
Yeah, can you say more about A?
A has to be geodesically convex. So if you take any two measures in the set and you have a geodesic interpolant between the two, the geodesic interpolant must stay in the set the entire time. So an example of such a set would be L1. So all of your measures have to admit a density. And if you take a geodesic interpolant between any two measures that admit a density, it still admits a density. So this would be one example. Another could be measures with some uniform bound on their second moment. So you pick R, you say all my measures have to have second moment R or less. This is also geophysically convex. Yeah. Are there any particular sets of interest that you are thinking
No, I
of?
think I get it now.
Okay.
There are some obvious choices, but you sort of have the general.
Yeah. Okay, so now what about the specific setting? I advertised this talk as gradient flows, and yet I do not see a gradient here. So as promised, we will look at also at the specific setting where you have a gradient flow. So now we're picking a choice of V, where V has the form gradient first variation. So this first variation is like a functional derivative with respect to rho, and then this gradient is a gradient over the space. So in the particular setting where you are doing a gradient flow with respect to your own measure, this is a gradient flow in species I. In this setting, we have a condition for lower semi-continuity. If this guy's basically smooth enough or has the right continuity properties, and your steady state is an A, then you can say that the steady state is the unique Nash equilibrium of F in A. So what this tells us is that if you do a gradient flow on a monotone set of energy functionals, you will converge to the Nash equilibrium. And so if you are in game theory and you want to know, I have this measure valued set of energies and I want to find a Nash, this gives you a way of actually finding the Nash and guaranteeing that you will converge to it. And so this is also a contribution on the game theory side because this type of gradient flow analysis had not been done as far as finding measure valued equilibrium. Most of the results now are on what we would call pure Nash, which is where each measure is like a single Dirac. And so this includes that, but is also extending to the general measure value setting. Okay, so yes.
Give an example of an energy functional that will satisfy the lambda non-density that would be interested in utilizing, or like this some kind of divergence that forms in this would satisfy this monodensity condition.
Yes. So actually the example I showed before, I don't know how far back this is. Yeah, okay. This is monotone with lambda equals 0. So it's lambda equals 0 because this is not lower bounded by a quadratic. But this cross-term structure and the zero-sum structure is actually monotone. So you can prove okay, this technically is degenerately monotone because lambda equals 0. There is also work that says it's close enough to being monotone that you can actually still get a rate. And this is something we discuss in the paper. So you can kind of think of this as almost monotone, and we show that because it's close enough, you can actually prove convergence of this. So what we would expect here is for these masses to kind of converge to some stationary distribution. Yeah. And that would happen from any initial condition. Does that answer your question? Okay. Yeah. Okay, so the takeaway from this is that monotonicity with positive lambda implies existence, and uniqueness, convergence to steady state. And so this is kind of one of the key results that we wanted to have for many of our applications. Another thing I'll discuss is the convergence of the velocities. So the velocity fields VI, we are now going to look at their 2-norm weighted by rho. And this is a commonly studied quantity in gradient flow analysis called the dissipation. For a single species, this is the time derivative of the energy. But in the multi-species setting, this is no longer true. But we still want to understand what this quantity does because it's very useful from an analysis perspective. And so recalling our finite dimensional analogy, if we look at our 2-norm of the velocity fields, but now we just weigh them by our measures, you can show a very similar result and treat this as an analogous Lyapunov function. Okay, so we show that if you have lambda monotonicity and you have a finite initial condition, that this guy converges exponentially also to 0. So what this is saying is that eventually your velocity fields go to 0. If this guy goes to 0, then dt rho goes to 0. This is not actually how you would prove convergence in W2 though, for reasons that if you would like to ask me later, I'm happy to discuss. Yes.
So you're saying that this only shows that you convert, oh, that this energy function for reasons that's not enough to use the two?
Yeah. Yeah, this is a weaker notion. Yeah. Okay. Okay, so now I want to spend some time and talk about the applications and kind of what we can learn from this analysis. So I'll start with our census data question. And the question is, can we model this as a gradient flow where now instead of modeling individuals evolving, we're modeling an entire distribution of people modeling and shifting to become this distribution? Okay. So the way I set this problem up, as I said, suppose this population is made up of some group of people who do not qualify for aid, so they're truly under or above the threshold. And there's some other quantity rho bar who do qualify, and they are under the threshold. However, we don't actually know the true underlying data because all of this data has been manipulated, as we know. Okay, so I will use our favorite log loss classifier to give this threshold a way of splitting the population into qualifies, does not qualify. So this is the probability of a agent at location U does not qualifying, given that the X parameter is the classifier parameter. Okay, and then you can just take 1 minus this to get the probability of being in the other population. Okay, so the classifier's goal is to minimize the loss. So they want to minimize the number of people who do not qualify and being classified incorrectly, and the people who do qualify being classified incorrectly. Okay. But the population, however, wants to be this guy. They want to be classified incorrectly because they want to qualify for aid, even if maybe they shouldn't. And then I have a penalty term here, which is a KL divergence term. And this basically says there's a penalty for rho deviating away from rho tilde. So this is like a penalty for lying. So saying you can lie, but there is a cost, or manipulate your data, even if you're not lying, but there is some sort of cost to this. And then I have an incentive here for having a lower poverty index score. I mean, having a lower poverty index score can never hurt you. So with these parameters fit by grad student descent to the data, okay, yes, this is our gradient flow. We're going to have our population rho minimize this energy. And we actually get a very good fit from 1995 to 1998. So our true data distribution, and this pretty simple and intuitive cost function shows how a population of people could be incentivized to manipulate their data to achieve some sort of desired outcome. And one of the things I just want to mention is this is the finite volume method that I used for implementing all of the illustrations in this paper. So this method basically like takes your domain, chops it into blocks, and then tracks how much probability mass should move into each neighboring box. And so it guarantees that you preserve mass. So there is a way of simulating this in 1 dimension and 2 dimensions with guarantees about how big your like dt versus your dx have to be to make sure that you preserve mass, which is very nice. And if anyone,
I'm sorry, can I ask a question? The parameters 0.1 and 0.06, are those chosen to make the fit even better? Like, are those hyperparameters?
Those are things that I tuned, yeah.
And presumably the orange and blue wouldn't fit quite as good. They would have the same qualitative with different parameters.
Yeah.
Okay.
Yeah, so I think the things I tuned were this, and this too.
Okay.
Yeah.
Okay, thank you.
So in the context of what you already presented, the contribution is knowing that it converges. You don't know a priori what it converges to.
Yes.
What the shape is.
Yeah. So if you know that you can also prove existence of a unique minimizer, and then you can use an Euler-Lagrange. So you can think of this as like setting the derivative equal to 0. You can use that to maybe say how smooth is my solution. Sometimes you can actually get a closed form solution for the minimizer if your energy has like gradient of f of x equals 0 is nice enough, but sometimes that equation is only implicit. So depending on what the Euler-Lagrange condition is, that tells you like how much you know about your steady state. So actually, going back to your question about what A is, you can often use the form of the Euler-Lagrange to say that your solution is L1, for example. And then even though L1 is not compact in W2, you still have the right property that you need for your steady state to then apply the next parts of the theorem. Yeah. I'm also happy to show an example of this if there's time. So that's kind of nice. And so one of the things that we're interested in doing in the future is now that we have a good model, so the government in this setting did not actually move their classifier. And the natural question, of course, is, okay, now I have a model for how people will behave. How do I update my classifier in a way that incentivizes people to behave according to whatever my objective is? And so I have some ideas for this, but if anyone is interested in discussing, control or as I wouldn't call it population control because that's not the best. But if anyone is interested in kind of looking at the next step of like how do you optimally solve for some trajectory for this guy, I have some ideas for that also. Okay, so let's look at optimal transport. So our optimal transport says if I have a point in this distribution, where do I move this point to in this distribution in a way that minimizes this cost function? So you can view this gamma xy as an instruction for given a point x, what point y does this map to? And in a way that minimizes some convex cost function c. And this notation here, as I mentioned before, means gamma has marginals mu and nu, but it could do kind of anything not on the marginals. Okay. So our idea, as before, was to solve this min-max problem. And this min-max problem has a Nash equilibrium that solves our optimal transport problem. And these guys are our marginals. So instead of making these constraints hold, which they do here, we have them be soft constraints, and then we increase over time, or we increase here to infinity, the weight of this penalty. So this KL term basically forces gamma 1 to be equal to mu and gamma 2 to be equal to nu in a measure sense. So almost everywhere. Okay. So actually, I'll be kind of comparing this to some results analyzed in this recent paper by Shiza for discrete annealing. So if anyone is familiar with optimal transport, this is definitely a paper that's related that you should look at because they get the same result as us, but in a completely different analysis perspective, which is pretty cool. Okay, so we're going to use the gradient flow, as I said before. So we are going to decrease f in gamma, and we are going to increase lambda, f in lambda. And you can view this as like a gradient descent ascent, so like a min-max problem. Okay, so how are we going to do this? For our analysis perspective, we are going to do kind of what is done sometimes in computation, where one of these is much faster than the other. So if my gradient descent is very, very fast relative to my gradient ascent in the other species, you can model this as at each time step, gamma is instantly minimizing for lambda. And so this happens if you look at, for example, an OT algorithm where you fixed your regularization parameter, you solve it, then you update your regularization parameter, you solve it again, and you do this because it's more numerically stable than just picking a really small regularizer to begin with. Okay, so this is what we analyze, and we are able to show that the fastest your lambda should update in this setting is order square root t. So if you're trying to solve your OT problem and you update your epsilon parameter too fast, people already know numerically, you do this too fast, you end up not getting the right answer because of errors. And what this is suggesting is that you should not update faster than this order of magnitude. And this is the same order of magnitude that Shiza in the other paper also obtained from a discrete time analysis and also a discrete setting analysis. And so this gives us kind of a practical guideline for, okay, I'm solving my OT problem. This is what my schedule should look like. Okay, and then what we also do in this work is compute optimal transport maps using a particle method. So that gradient flow that I showed over here, yeah, this guy, we can approximate this with particles for the density. So instead of having a measure, you can actually approximate a bunch of particles that have that same distribution and evolve those particles forward. So we use an algorithm for this. And I'll show you kind of how this looks over time. I have two sets of particles, one initialized at my source and one at my target. And over time, they flow to the correct opposing distribution. So the goal of this here is to have some interpolation between this distribution and this distribution, which you can see here, which minimizes some total amount of movement. And what I did was start a bunch of particles according to this distribution here. And then all of these particles I started according to this distribution, and I have them flow to their opposing targets. And this gives us a practical algorithm for solving this optimal transport question. One of the features of this, so maybe I think Bomdad might be familiar with some of these, is if you solve an OT problem with samples, your map is constrained to having only support on your actual samples. But if you use a particle method, then you're not constrained based on your samples. So that was one of our goals in using this particular method. Did someone have a question on Zoom?
Yes, maybe a quick question, like maybe a slide 25. Yeah, so the formulation says like you're adding both of the regularizer, but we are doing a min max. Is that the typo or I'm missing something? Like I thought like if you're minimizing, it's okay that you do. I see it's minimization with respect to both of gamma 1 and gamma 2, but
It's minimization with respect to gamma. Oh, sorry. So because we're minimizing with respect to gamma, we are doing a gradient descent here.
I see. Because the way I remember the Chizat's result is that one of the regularizer should be positive, the other one is negative, and that makes sense because you're doing sort of a min max, but that I couldn't see it here, so probably.
Oh, I think so. He in his paper. So the question was in the Chizat paper. There were multiple regularization schemes, and one the regularizer was increasing, and one it was decreasing. That was a slightly different setting than this.
I see. Okay, so
I'm happy to discuss that one also. Because
yeah, got it. Yes, got it. All right.
Yeah. Okay. So, okay, now let's talk about banking and loan applicants. Okay, so you have multiple banks, and they are offering new accounts, new loans, various services. And you have two populations of people who are applying for such accounts or such loans or purchasing services from these two banks. And we will parameterize their incentives by these cost functions F. And looking at the bank's cost function, the banks want to minimize some loss that is a function of this population. So if I provide services to population 1, this is how much I gain or lose, and I want to minimize this. And then if I provide services to population 2, this is my loss. And then for the banks, they have some utility or usefulness of purchasing from bank 1, and this is this H1. They have some sort of usefulness from purchasing from bank 2, which is this function here. We have some sort of nonlinear interaction kernel here. So what this models is if I talk to someone else and I hear, oh, you applied with these parameters and you got this output, then that means I'm going to try to manipulate my data to be more like you. That would be an example of an attractive kernel. Or if I say, oh, you applied and you didn't get approved, I'm going to be repulsed from your data, not you in particular. And so you can actually model the ways in which people are incentivized to become more similar or less similar to others in the distribution with this interaction kernel. And just as kind of a fun aside, this is also how many folks in math biology model swarms. So birds are attracted to birds that are far away from them, so they stay in one large pack, but they're repulsed from birds that are close to them because they don't want to have any collisions. And so actually a lot of the same mathematical models we can apply in this particular setting. And then we also have some regularization or penalty terms that say, you know, there is a cost for changing either your bank parameters for your classifier, or if you're a population, you have to stay somewhat close to some reference measure. So this could be your initial condition that kind of says, okay, you can manipulate your data, but you have a penalty for either lying or for changing your information. And I'm gonna split the banks and the people into kind of two different categories. So one bank, as I showed at the beginning, will have a really bad initial condition. The classifier will be completely wrong, and they will be giving loans and new accounts to bots or manipulative individuals. There's another bank that has a good initial condition. It has a line that pretty well separates our two populations. We have one fraudulent population, which could be people or agents, and then we have one valid population. Okay, so if you kind of zoom out from this is a game with 4 players. You have 2 banks, and you have 2 banks here, 2 populations, and they're all doing gradient descent with respect to their own value. So this is gradient with respect to row 1, gradient with respect to row 2, gradient with respect to H1, gradient with respect to H2 of their own functions. And each of these 4 can be completely different. So what you would do then is take your Fs and plug them into your monotonicity condition and check, is this monotone? Do I expect to converge to a steady state? If it's not monotone, is it close? And there are, that's also another interesting direction where, you know, looking at perturbation type results. Okay, so I'm going to compare 2 settings, one where you have no interaction kernel and one where you have an attractive repulsive kernel. And we're going to see kind of how this kernel impacts the evolution. So, and as I said, these lines are kind of the 50% threshold. So of where your probability of being classified is exactly the same on either side. Okay, so at t=6, we see here this population splits into 2 kind of modes, whereas this population does not. So here, this entire mode is going to be classified desirably according to them, which is incorrect. I mean, so this is your fraudulent population. They should not be getting a loan or an account, but here they are being on the correct side of this line. But you do see the classifier in both cases is kind of correcting very similarly. They're kind of trying to reorient themselves to be correct. Okay, next time step, you see kind of the same behavior where you have this multimodal distribution here, but not as much here. And by the time you get to the steady state, they're actually very similar. And so if you are looking at these 2 densities from start to finish, you might say, why do you even care if you model this interaction here at all? And the answer is really, if you look at which bank does worse and by how much. So actually, if you look at this setting and you compute the loss over time based on how many individuals qualify, the bank actually does, bank 1 does significantly worse in this setting than in this setting. But this is not obvious just looking at the initial and the terminal conditions, and it's also not necessarily obvious just looking at the distributions. Yes.
Yeah, only the populations have the kernels, not banks.
Yeah.
They can't
No. Yeah. Although that'd be fun. Yeah. And so what this is telling you is that a lot of models in machine learning, they model, okay, this is the mean, this is the variance of some distribution that I'm applying my classifier to, and it's evolving over time, and I'm going to track the mean and the variance. But what this is showing you is that if you have a competitive setting, you really need to be modeling more than just the mean and variance, and you could actually care about the distribution, because even though these would have very similar means and variances, the actual performance of the classifier is quite different. And so this is why using these new modeling techniques is important if you want to be deploying your learning algorithms on strategic agents. Yes, so distribution level modeling is important and we should care about it. Okay, so takeaways, what are the 3 takeaways from these 3 applications? One is that you can actually model strategic behavior by a PDE, and this was kind of the first step that I took in this line of work. Second, you should account for non-local interactions. And we've shown this in a couple different settings. This bank setting is one of them. And finally, if you pose these optimal transport problems as min-max flows, you can actually have insights into practical algorithm rates. So, how fast do I update my regularizer if I'm trying to solve this on a computer? So current work, one is allowing the individuals to switch species. So you could imagine instead in the bank scenario that instead of modeling species as just fraudulent and not fraudulent, you also model them by which bank they are a customer at. Because here, I didn't actually specify for each part of the density, oh, are you a customer at this bank or this bank? And often people will be a customer at a certain firm or provider, and then switch based on the benefits that other providers have. And so this not only has a very nice mathematical structure, but also has, applications in how people are incentivized to purchase. Existence of solutions. I'm very excited about this. It's very fun and it's very, very mathematical, but we are working on proving existence of solutions of all of this. So we kind of assumed it's all there, but we didn't prove it, and now we're proving it. And then one of the other things we're really interested in is learning these PD dynamics from data. So if you're going to be using a PDE model to say, how should my government update its aid threshold, you better be sure that your model is good and that it's correct. And so we need to have something other than, a grad student fitting data by hand. So, something with guarantees, something with that we can say we're able to make decisions based off of this. And so, I'll talk with some folks here about this, but if anyone is interested in learning PD dynamics from data, I have some applications for that. And again, we kind of want to generalize this theory, as I said, to metric spaces. So now that we did monotonicity in one metric space, which is Foster sign 2, we're now looking at, okay, what does this look like in any generic metric space? And so all of this looks like it will generalize, but that's something I'm working on. And then again, if you want to have any sort of real life implementation of this, you really need to make sure your model is correct. So having rigorous ways of learning these dynamics would be very important. That's all I have. If anyone wants to see some proofs, I have proofs, but I'll probably take questions first.
Thank you so much for that talk. Are there any questions for Lauren?
Yes.
So your definition of monotonicity is, to me, it's a little bit tricky.
Okay.
So do you have like there's some lemmas or maybe calculus of like how I can build monotone X? As in like, for example, like if I take a bunch of convex F's in their own rows,
Yes.
that should work.
Not necessarily. So I do actually have, we do have a number of lemmas for these. So if each species is monotone or convex in itself and not coupled, it's monotone and completely uncoupled.
Not coupled.
Oh, then yes.
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 But then like, are there simple perturbations of that I can do? It's just affine coupling or something. I don't know.
Yes, exactly.
Some
Yes.
perturbations that preserve monotonicity, so I can like build them up from
Yes, exactly. So we have additivity. So if you take like something monotone and you add uncoupled convex, stays monotone. We also have a lemma that says if you're convex enough in your own energy and you have Lipschitz bounds on the gradients of the other players with respect to you, you look at that entire matrix of like the diagonal is my convexity, the off diagonals are Lipschitz bounds on how much the other players affect me. And if this whole guy has eigenvalues that are positive, then it's monotone. And this is something that we lifted from like finite dimensional contraction theory. And it actually works very well with the attractive repulsive kernels because those satisfy that Lipschitz bound. So you just have to make the magnitude of those interaction terms small enough and then you still have monotonicity. Yeah. Yes.
Really wonderful collection of results. I'm interested in the applications. How interested are you in moving from kind of descriptive to more prescriptive? And I'm wondering if the bottom right corner there gets at what I'm thinking.
Yes, exactly. So prescriptive to me can happen if you know your models are correct and good enough. I definitely think it would be worthwhile to use this information to try to have policies that are fair and policies that are kind of incentivize people to not shift their data as much. And so depending on what kind of metric you want to minimize, so say like minimize the amount of movement in your data. So you want to make people not feel like they need to manipulate things. Or if you want to say like there's no subpopulation that is like disproportionately affected compared to other subpopulations. These optimization problems are very interesting and they're infinite dimensional. So there's lots of opportunities for nice new math as well for that. Like this would just be the start of kind of solving those problems. Yeah.
I have a couple questions and thanks for the great talk. So you're proving results for convergence to a steady state.
Mhm.
Do you think you could generalize this to convergence to other types of attractors, like, periodic solution?
Oh, like an
or
orbit or a set?
Something like that, yeah.
I think so. I mean, our second moment result, for example, is convergence to a ball. And then you could be inside that ball, who knows? I would definitely, I mean, I have to think about it, but I bet I would be optimistic, I think. Yeah.
One more quick question. How do you think this general analysis scales with the number of species? Because I'm thinking about, like, do you apply this to financial markets, similar to financial regulation, where there might be more players?
I think the theory scales. I don't know about the computation. What specifically for the computation?
I'm not sure, just your general thoughts on, like, can you apply this to multis, like to many more species?
If you had some knowledge about maybe you only interact with local neighbors, then I think you could do it. So if I as a gradient descenter only need my like neighbor's information to compute my gradient descent, then I could say if I have knowledge of the whole system ahead of time that says the system is monotone, then I don't need global information to still run gradient descent. But you would still need some sort of global knowledge of the system in order to say whether you would converge to something. Yeah.
Thanks for the great talk. I have a question about the future direction.
Oh, yes.
Do you think for 4D part with the kinetic?
Yes. So adding, so you would have your flow term, and then you would have a term that has like some scalar times my species rho j, different scalar times my species rho I, and you have some sort of, global mass conservation requirement, but I would view this more as like, on one level, you have a gradient flow in W2 for each species, but on a higher level, you have a gradient flow on a graph among all of the species. So if you were to just, instead of modeling each species as a distribution, you just model them as a point on a graph, and then you ask how mass like flows across a graph, that is actually a gradient flow, just in a discrete sense. And there are other results that allow for gradient flows on discrete settings. And so you can kind of think of that as more of like a bi-level graph gradient flow combined with a W2 gradient flow. We can talk more, about that. I think that's a very interesting question, although gradient flows on graphs showing long time behavior is much harder. Yeah.
There's one question on Zoom from Marco. Is the search for the convergence of solutions a planned precursor to finding metrics for controllability?
Oh. Let's see. Is the search for... Oh, nice. That's an interesting question. I haven't thought about that. Having controllability, so controllability for these gradient flows has been studied in the math literature, and the results are of the flavor. There exists a controller, and it is in H2, and that's all we know. So I think as far as actually practically solving for controllers, that gap has not been filled at all. So there would be a lot of opportunity and space for like taking this to say, how controllable is my system? But the hard thing about controlling these infinite dimensional systems is what class you restrict your controller to. So do I restrict my controller to everything that's C2? Or do I, is my controller, like, what function space is it in? And then, what does this mean for my solution? And am I looking at weak solutions? Am I looking at strong solutions? Like the amount that you have to define and kind of restrict yourself to what question you're asking becomes much more complicated. Yeah.
Right, well, let's look at our speaker one more time.